Justin Josephus is presently an associate professor in the Department of Physics at the NIT Tiruchirappalli, Tamil Nadu. He received his PhD in the area of nanocrystalline magnetic materials from the University of Madras. He pursued his postdoctoral research in Tohoku University, Sendai, Japan. He has undergone specialized training in electron microscopic techniques from University of Pune, thermal analysis from IIT Madras, computer simulations from Madurai Kamaraj University, in vitro cell culture from King's Institute, Chennai, besides hands-on training from the Defense Metallurgical Research Laboratory, DMRL, DRDO Hyderabad, and Baba Atomic Research Center, Mumbai, Getwell Hospitals, Tamil Nadu, etc. He joined the Department of Physics as faculty and has over 2 decades of teaching and research experience. He has published more than 50 research articles in internationally reputed journals. He has presented his research work in more than 40 international and national conferences and has made presentations very widely in countries such as USA, Japan, Singapore, Canada, Spain, Slovakia, and so on. He has organized and participated in various seminars in his areas of specialization. He has contributed various chapters in many popular books. He has immensely contributed to research on soft and hard magnetic materials. His current research interest is to obtain enhanced magnetic properties in nanoparticles. Research area of interest include polyol processes, magnetic nanoparticles, Moss-Beer spectroscopy, magnetic nanoparticles, particle hypothermia, ferrous-based alloys, etc. He has undertaken research projects on development of magnetic nanoparticle suitable for detoxification and drug delivery from the Department of Science and Technology, synthesis and characterization of nanomaterial for engineering applications with funding from DST Nano Mission. On a project visit, he undertook a study on the order-disorder studies in chemically synthesized FeCO alloy through DST KEK Tsukuba, Japan. He was a recipient of UGC Fellowship, Senior Research Fellowship from CSIR, MEXT Research Fellowship from Japan, COE Fellowship from Japan, and secured the Best Poster Award at ISHR and ICSTR in 2006 in Japan. He obtained the illustrious postdoctoral fellowship in the Graduate School of Environmental Studies, Tohoku University, Sendai, Japan, and he is a certified chartered physicist by the Institute of Physics, United Kingdom. He is a member of the Indian Physics Association, Magnetics Society of India, Materials Research Society of India, Indian Society for Non-Destructive Testing, and is the elected member of the Institute of Physics UK since 2011. And with this brief introduction, I would like to hand over the platform to Professor Justin Josephus to facilitate the session on emerging applications of magnetic nanoparticles. Over to you, sir. Thank you very much.
Thank you, Shri David Paul. So I also thank the organizing committee for choosing me to deliver this talk. So I will share my slide.
Yes, sir. In fact, it's our honor to have you, sir.
Yeah, thank you. Thank you, actually. Actually, I should also tell you that, I am here in place of Dr. Shiba due to some reason or the other. Her talk will be later on.
Yes, sir. Yes, sir.
I have interchanged her session.
Correct, sir. Yes, sir. Yes, sir. Visible, sir.
Okay. So if my voice is not audible or if you...
I will let you know, sir.
Okay. Thank you.
Yes.
So I also wanted to ask, what is the composition of the participants, from which discipline?
Sir, most of them are students beginning their careers in engineering, science, and technology. basically from about 30 states, including Northeast. And these are budding engineers and postgraduate students in science. So most of them, sir. And there are many students from NITs, IITs, and industrial technological institutions across the country.
What about their discipline background?
Sir, there are, it is a heterogeneous background, sir. They are from computer science, they are from biological sciences, chemistry, physics, and various other fields, sir. So it's not a homogeneous group.
So one more thing is, is there any session after my session, or is there?
No, sir. Yours is the final session for today, sir.
Okay, thank you for the
Thank
information. So I think from what Sri David Paul has told, it is a multidisciplinary environment. So I think the subject which I am going to deal with is also a multidisciplinary topic, which includes physics, chemistry, as well as partially biology also. Okay. And of course, you may have had an introduction about nanotechnology and what are the possibilities. But I am specifically going inside application of magnetic nanoparticles with starting from the fundamentals, because of course, physics will be for all. So most of you might have come across physics topic in +2, and then only you might have joined the engineering. So in that sense, I think most of you can understand physics, chemistry, and maybe biology may be something difficult, but you may have learned it in the lower classes. We are not going to deal with any biology which is too high, too high level. So emerging application of magnetic nanoparticles. So I come from NIT and from the Department of Physics. So you can easily understand physics oriented talk. And also I am also into the magnetism group, and we have our own magnetic materials group in LinkedIn. So if any of you are interested in magnetic material research, then you can join there, where we have more than 500 participants world over, which includes company CEOs and scientists and technologists. Okay. So now coming to the contents, I have arranged it in such a way that I will give you a brief introduction about magnetism, introduction to magnetic nanoparticles, and also a few applications, especially from our lab. Okay. So what is the origin of magnetism? Okay, so from the classical point of view, any charged particle which is in motion, that will produce a magnetic moment. Not only magnetic moment, it will also produce a magnetic field. Okay, so what you have here is an electron which is moving around the nucleus. Okay. Of course, this is not to scale. Okay, so here charged particle in motion will produce magnetic moment, which is given by magnetic moment mu equal to I into A. I is the current, A is the cross-sectional area. So charged particle electron, which is moving around the nucleus, will produce a magnetic moment, and this can be imagined as a current loop. Electron moving around the nucleus can be imagined as a current loop, and that will produce a magnetic moment, which is known as the orbital magnetic moment. Then you have another quantum number, spin quantum number. So from the spin quantum number, experiments have shown that electrons also possess a spin magnetic moment. So the sum of the orbital magnetic moment plus the spin magnetic moment will contribute to the total magnetic moment of an electron. Underline electron. Okay, and this magnetic moment, which is the smallest possible magnetic moment, is given by mu b Bohr magneton, which is mu b equal to EH cross by 2m, where E is the charge of the electron and m is the mass of the electron. So magnetic moment is inversely proportional to the mass of the elementary particle. So if you consider another particle, which is proton, and the mass is heavier than the electron. So the magnetic moment produced by the proton is much, much smaller. So you can note that 10 power minus 27 kg for order of 10 power minus 27 kg for the proton, 10 power minus 31 kg for the electron. So you can imagine the order difference. So when we discuss about magnetic properties, we discuss about magnetic properties contributed by only the electron. We neglect the contribution by the proton because of this reason. Okay. But an atom has not one electron. One electron has contribution due to orbital and spin magnetic moment. But one atom has more than one electron. Okay, an atom can have make simplest hydrogen is one electron. But other atoms, no, you can consider like any other atom. So it will give a magnetic moment due to the sum and orbital motion of the sum of the orbital motion of the orbital motion plus the spin motion of one electron. So if you have like multi-electron, then you have to count the total angular momentum. So the total angular momentum is given by J, okay, which is equal to orbital plus or minus S. Okay. So it is not a simple sum or subtraction rule. It is governed by Hund's rule, which states that if you are having less than half full, it is L minus S, and if it is more than half full, it is L plus S. So the net magnetic moment contribution by an atom is given by the sum of the magnetic moment contribution due to the electrons which are present in it, and that is G into mu G into J into mu B. Mu B is the Bohr magneton. J is the total quantum number value, which is the sum of the orbital and the spin quantum numbers, and G is the G factor. So that will give rise to the total magnetic moment of an atom. Okay. So the condition for the magnetism is that there should be an electron which is unpaired. Okay. So unpaired electron will give rise to a net magnetic moment. So if you have paired electron, what will happen? A spin which is up and another spin which is down. So one mu B from up spin and another one mu B which is in the negative direction. So these two will cancel each other. So an atom cannot have a magnetic moment if the electrons are contributing to the anti-parallel alignment. If the anti-parallel alignment comes due to Pauli's exclusion principle that we know very well. Okay. So this is a very, very fundamental thing which anyone has to understand. Everyone has to understand about the origin of magnetism is the unpaired electrons which are contributed by the magnetic moment of the electrons. Okay. So now coming to the next topic, certain elements are ferromagnetic, certain are antiferromagnetic, certain are para, and certain are dia. So what is the reason for ferro? What is the reason for antiferro? So this picture in slide 4, I am just representing here. So the red ones are the atoms. Okay, so the red ones are the atoms, and the blue arrow that represents the magnetic moment direction. Okay. So how can you get the magnetic moment? I told you Gj mu B. Okay. So sum of the magnetic moments of the electrons following the Hund's rule. Okay. So now if you have a crystal, there are a lot of atoms in the crystal. So neighboring atoms, if they are aligned parallel, then it is ferro. And if it is aligned anti-parallel, this is antiferro. This all very well known. We all know what so. When will be an atom behave ferromagnetically and when will it become antiferromagnetically? So if two atoms are brought closer together, okay, if their interatomic distance are optimum, if they are not too close to each other, then they will be ferromagnetic. So one atom will be contributing to a magnetic moment up. Another atom, when you be bringing them closer, it will also be acting in the up direction. So that is ferromagnetic. So now when you make the distance much closer, when you make it much closer, what happens? They will behave in the antiferromagnetic sense. Why? Because of Pauli's exclusion principle. When you bring two atoms closer and closer, atoms are having electrons in it. So there is a lot of Coulombic repulsion because of the like charges, negative charge of the electron. So when you bring these atoms closer, what will happen? The electrons wave function will overlap. This is the quantum mechanical sense. So those who have not gone through quantum mechanics, don't worry. So you think in the classical sense, like no, these electrons will repel, try to repel each other. So they will stay in the minimum energy state, obeying Pauli's exclusion principle. If one of the quantum number is different, that is the spin. So what will happen? The spin will get reversed. So that is why we get antiferromagnetism. So the origin of the ferromagnetism and antiferromagnetism is due to a parameter known as the exchange interaction. Remember, this J is different. So the J here is not the total angular momentum, but that is known as the exchange interaction. That exchange interaction, exchange integral, if it is positive, it is ferromagnetic, and if it is negative, it is antiferromagnetic. So if you are having a negative J value, and if the interatomic distance they are much closer, that will be antiferromagnetic. Okay, so antiferromagnetic spins, both the magnetic moments will be same, but direction is different. Okay, in the opposite sense. So they will cancel each other, resulting in a zero magnetization result. Okay, but strictly speaking, no, the susceptibility is not zero. So we are not going in depth into it. What we have you have to understand is no, what is the origin of magnetism? Why do certain materials behave in the ferromagnetic wave and antiferromagnetic wave? We are interested only in ferromagnetic and ferrimagnetic material. So we will choose this ferro and ferrimagnetic material in the future discussions, because ferromagnetic material only will give rise to a magnetic moment. Antiferromagnetic, both of them are getting cancelled, so zero magnetization. And in the ferrimagnetic case, you are having one is larger than the other one, as shown here. So we will be having a net magnetization. So that will be also magnetic. Diamagnetic also, there is no magnetization. So we will proceed further with the ferro and ferrimagnetic material for further discussion. I hope now you have understood about ferromagnetism, antiferromagnetism, and its origin. Okay. So now coming to the types of magnetic materials, now I am just discussing about ferro and ferri. So we can classify them as soft magnetic material and hard magnetic material. So soft magnetic materials are materials whose coercivity is very, very low. So coercivity means no, any magnetic material will exhibit hysteresis loop. So if you apply a magnetic field, so you have a magnetic moment like this, direction is, let's say, up. So now if you apply a magnetic field, if you apply a field from the up to the down direction, the magnetic moment will also turn along the field direction. Okay. So that behavior with an applied magnetic field will give rise to a hysteresis phenomena that's shown here. So how strong you want to give a field to turn the magnetization in this direction. So that will determine the coercivity. So if you require large magnetic field to turn the direction in the opposite way, then the coercivity will be large. The breadth of the hysteresis loop will be large. So your hysteresis loop will become broader. So those materials which exhibit a broad hysteresis loop, that is they are known as hard magnetic materials, and those materials which are exhibiting very narrow hysteresis loop or low coercivity, they are known as soft magnetic materials. Examples are also listed here. The well-known example of ferromagnetic soft magnetic materials are iron, cobalt, iron, nickel, iron, and hard magnetic materials, alnico, samarium, cobalt, and NdFeB. You don't have any other choice other than this. Please remember. Okay. And magnitude of coercivity. Okay. What will be the magnitude of coercivity? Okay. So that will be determined by the constant known as anisotropy constant. Okay. The direction of magnetization. Okay. The direction of magnetization, that is only anisotropy constant K. So the K value determines the direction of easy magnetization. Okay. So if your K value is very, very large, then K is Hc, the coercivity is proportional to K. Okay. So it is like this. So I am just explaining these fundamentals because this is very, very important for you to understand the concepts regarding. I will just try to explain it. Okay. I cannot draw. Okay. So if you have a large K, your coercivity will be very large. If your coercivity is very large, breadth of the hysteresis loop will be large. So they are used as magnets. So the magnets which are sticking, right? Like the fridge magnets. So those are permanent magnetic materials. Very hard to magnetize, very hard to demagnetize. Soft magnetic materials are easy to magnetize and easy to demagnetize. Okay. And the fixed direction, which direction it is pointing, that is determined by the K value, anisotropy constant K value. Okay. So if your K value is easy or minimum along this direction, then your magnetic moment direction will be up. If your K value is minimum along, let's say 90 degree, then your magnetization direction will be along 90 degree. So the K value only determines the direction of easy magnetization. Okay. So having known this, we will go on to magnetic nanoparticles. Okay. So magnetic materials we know ferro, ferri, antiferro, dia as well as para. Okay. Para means the direction can be random. Okay. So magnetic nanoparticles. So if you have a bulk material, very big material, the direction of magnetization is fixed like this. Okay. The K value, anisotropy constant K value has the unit of joule per meter cube. Okay. So if you multiply with the volume, joule per meter cube into meter cube, so that will be the energy. So kV is the energy known as the anisotropy energy. So kV is the anisotropy energy. Then obviously we all know very well the thermal energy, that is kBT. Okay. So if kV is greater than the thermal energy, the magnetization direction will be fixed along the particular axis. Okay. But if the volume is reduced, when can you reduce the volume? If you reduce the size of the particle. What is a nanoparticle? A nanoparticle is a particle whose diameter is around less than 100 nanometer. So when you reduce the size of the nanoparticle, okay, when you reduce the diameter of the nanoparticle, what will happen? The volume is getting reduced. When the volume is getting reduced, the kV, anisotropy energy, that is also getting reduced because kV is the product of anisotropy constant into volume. Okay. So when you get this condition, kV less than kBT, thermal energy, what will happen? Your magnetization direction is not stable. Because the thermal energy is now trying to fluctuate the magnetization direction. This is known as superferromagnetism. So in addition to ferromagnetism or ferrimagnetism, we have another magnetic phenomena known as superparamagnetism, where the magnetic moment direction is not stable, but it tries to fluctuate between two minimum energy states. So as a result, you have the fluctuation, not a stable magnetization direction, but a fluctuating direction. So this is known as superparamagnetism, which is used in variety of applications, nanotechnological applications. The superparamagnetic phenomena is used in variety of. So from this, we will move on to the next slide. So we have seen about ferromagnetism. We have seen about magnetic materials, type of magnetic materials. Okay. So now how these are used in applications. Okay. So you very well know that you have hard disk in your laptop or computer. You have hard disk, and you need if you want to store a lot of videos and something, you need a lot of space. Okay. So if you want to store information, you can store information in the form of bits, like 1010. They are bits. Okay. And you can store electrical storage. 1 bit, like say 5 volt, and 0 bit is 0 volt. Okay. Optical storage, CD, DVD. Optical storage, if there is light, it is, let's say, 1. If there is no light, then we say 0. In the case of magnetic storage, if it is north, we say it is 1. And if it is south, we can say it is 0, or vice versa. Okay. So now if I want to store 1 bit, let's say I have to have a magnetization in the up direction. You can apply a magnetic field and you can turn the magnetization direction in the up direction. And the north is now, let's say, 1 bit. Okay. So now if I want to record 0 bit, okay, what will happen? You have to apply an opposite magnetic field. So the magnetization direction will be reversed. So what will happen? You will have a 0 bit. So now you have 1 bit with the north at the top and 0 bit with the south at the top. So you can alternatively record bits of 10100 or 1 or whatever information according to the direction of magnetization. Okay. So now you can see here the square box. So they are all particles which are north and south. You can say like no north, red dot is north and blue dot is south. So that means no, I am storing information in the form of zeros and ones. Now if I want to store more information, I want more such dots. Okay, so each dot correspond to a nanoparticle. So if you have a lot of such nanoparticles, then your recording density, you can record more bits and you can store more information. But there is a problem here. Okay, so if you reduce the size, I told you when you reduce the size of the nanoparticle, what you are getting is no a super paramagnetic phenomenon. That means now your magnetic moment direction is not stable. For a recording, now if I record 1 bit of information, it should be 1 bit even if you read it after 10 years. Okay. So if you are having a magnetic bit, a small nanoparticle which is below the critical superparamagnetic size, and if you record 1 bit, okay, so you apply magnetic field and you change the direction and record to 0. And if you remove the magnetic field, what will happen? It will fluctuate. It is now no longer 1 or 0. It is fluctuating. So we don't want such information loss. Okay. So that is one limit which is faced by the industry. So we want to destroy the superparamagnetic effect in the recording industry. Remember, not everywhere, in the recording industry. In the recording industry, we don't want superparamagnetic nanoparticles. We need stable ferromagnetic nanoparticles which are very, very, very small. Then we can increase the storage capacity. Okay. So for a small calculation, you can see like no, the simple formula can be used. Kv equal to 25 kBt, and you can find the volume of the particle at which no the particle becomes superparamagnetic. So from this no you can find the size. For the FePt, iron platinum with a K value, anisotropy constant value of 6.6 megajoule per meter cube, you get a radius of 2 nanometer and a size diameter of 4 nanometer. That means no below 4 nanometer, the iron platinum will be superparamagnetic. So that is the limit at which you can make a particle very, very small for recording applications. So you want a particle to be above 4 nanometer, especially iron platinum, to be above 4 nanometer in order to have a stable bit. Okay, but there are a lot of practical difficulties to achieve this, even this small size. So that is a very, very challenge faced by the industry as of now. So people are moving towards other alternative recording technologies. So your hard disk technology is slowly, it is not as fast as some 5 to 10 years back. It is slowing down because of the superparamagnetic limit. Okay. So you see here in this picture, there are a lot of small particles. So they are all nanoparticles. You can see the scale bar 30 nanometer. They are all small size iron platinum nanoparticles. Okay. So now I told you about superparamagnetism. Okay, that is one of the consequence of size reduction when you make the particle size to very small. So what are the other effects when you make a particle to nano? Okay, so let's say you have an antiferromagnetic material. So if you have an antiferromagnetic material, your net magnetization is 0. Okay, so provided you are below the Néel temperature. So what is Néel temperature? Néel temperature is the temperature above which an antiferromagnetic material becomes paramagnetic. What is Curie temperature? Curie temperature is temperature above which a ferromagnetic or ferrimagnetic material will become paramagnetic. So if you want to have a ferromagnetic material, then you have to be in the temperature below the Curie temperature. Or if you want to have a very good magnetization cancellation, then you need a temperature below the Néel temperature. Okay. So below the Néel, let us assume that ideally let us assume that the magnetization is 0. And when you make the size to very, very small, when you make the nano size, there will be a lot of atoms at the surface. So if you have a big volume, very big volume of a single particle, and if you make it nano, you can put more than 3 or 4 nanoparticles in that same volume. So what happens is surface area becomes very large. So there will be lot of magnetic spins. Magnetic spins means the atoms which are having a magnetic moment. So there will be atoms at the surface. So surface atom, there will not be any interaction between the surface atom and the air. So there will be magnetic exchange interaction between the atoms only at the interior. So what will happen? You will have an atoms which are pointing at a random direction at the surface. So that will give rise to a net magnetization. So remember, an antiferromagnetic material will behave like a ferromagnetic material when you make it nano. Okay? But in fact, no, it is an antiferromagnetic material. But the surface atoms are disoriented, so you will get a superparamagnetic like behavior. So example, very well known example is nickel oxide. Okay? So now let us move on to ferromagnetic material. So we have seen antiferromagnetic material in which they may behave like is it okay? Screen is visible?
Yes, sir.
Okay. So magnetic properties of nano Fe3O4. Now that is magnetite. Magnetite means ferromagnetic material. So your magnetization is maximum for a bulk material. Okay. Due to this surface atoms which are disoriented, your magnetization comes down for a ferromagnetic or ferromagnetic material. Okay. So the magnetization will come down for ferrites such as Fe3O4 as the particle size is reduced. So when you make a nano, your magnetization is coming down because of the surface atoms which are disoriented. So coming to the coercivity, what will happen to the coercivity? Coercivity is the breadth of the hysteresis loop. So coercivity also will come down due to superparamagnetism, because superparamagnetism is the fluctuation in the magnetization direction. So that will give rise to a zero coercivity. So your coercivity also will come down. So these are some of the changes encountered in nanomagnetic materials. Okay. So now let us see how we can measure the magnetic properties of these materials. How we can measure the magnetic properties. So it is measured using an instrument known as vibrating sample magnetometer. From the name itself, you can understand that it is vibrating sample. Sample is vibrating. Magnetometer is a magnetic measurement instrument. Okay, it measures the induced EMF. So you have here an electromagnet which is placed and the sample is placed in between the electromagnet and the sample is in the rod and it is connected to a head drive loudspeaker like mechanism. So you give an electrical signal and you will vibrate the head drive, and that vibration will make the sample to move linearly up and down. Okay, in between this electromagnet, the electromagnet is producing a magnetic field which is given by H equal to Ni by L. Okay, so in N number of times I current, okay, by L is the distance of the solenoid. Okay, so if your sample is subjected to magnetic field, it will induce an EMF according to Lenz's law. You know very well Lenz's law. So if you have a coil and if you have a magnet and if you put the bar magnet inside the coil, it will produce an EMF and you will show an deflection. That's a very well known school level experiment. So that is due to the Lenz's law effect. So according to the strength of the magnetic moment, your induced EMF will be also, voltage will be also vary. Okay, so let's say 5 volt is equal to 5 EMU, then 1 volt is equal to 1 EMU. So likewise, you can calibrate and you can measure the magnetization, which is plotted in the y-axis, and the x-axis we have the applied magnetic field produced by the electromagnet. Okay, so in this way we can measure the hysteresis loop. And this slide number 13 shows you the hysteresis loop of magnetic material. So, which is NdFeB. So, in the NdFeB has a high K value. So, you can have a very broad hysteresis loop. NdFeB is the strongest known permanent magnetic material in the world. Okay. So, you can have NdFeB, which can be used as a very good permanent magnet. Okay. Now, sometimes, if you have a permanent magnet and if you put it in a steel, you cannot take out. Okay. So, that is difficult. So, if you consider the same COPT and if you make the size to, let's say, 5 nanometer, okay, when you make the size to 5 nanometer, COPT is also a permanent magnetic material, but when you reduce the size, the coercivity comes down. Now it is behaving like a soft magnetic material. Okay, you can increase the coercivity a little bit by increasing the fraction of hot magnetic phase by using copper. So you can see the effect of copper. When you put copper 10, it increases the K value, effective K value. So your coercivity increases. Okay. So you can, why we need to increase the coercivity? Why we need to get a larger K? Because for recording applications, we need larger K, otherwise your bits will not be stable. So we need small particles, but small particles with large K, large coercivity. Okay, so that is one approach where you can increase the coercivity or increase the K value, okay, using substitution. Okay. Now, we need high K material. So high K material will produce a broad hysteresis loop, but the magnetization will not be very large. Soft magnetic materials will have large magnetization, but small coercivity. Hard magnetic material will have large coercivity, but small magnetization. So what about combining these two? So when you combine these two, you will have high magnetization from the soft magnetic material. We can have high coercivity from the hard magnetic material. You can make a composite, but the size of the particle should be as small as possible in order to have this effect. Otherwise, it will behave like individual mixture. Individual mixture in the sense like it will show the red behavior as well as the dark blue behavior. We expect the dotted line behavior where you get the effect of both the magnetization and the coercivity, and you get somewhat a square type of hysteresis loop. So far, there has not been much success. Okay? So you see the practical BH max. BH max is the second quadrant area in the hysteresis loop. Okay, so the second quadrant, first quadrant and second quadrant, the left side, top. So that area should be as large as possible in order to have large energy product. So if you are having a large energy product, the magnet will be strong and the size of the magnet can be very, very small. So the practical BH max of NdFeB, the strongest known magnet, is 65 megagauss Oyster. Okay. Theoretically, it is predicted that you can get up to 120 megagauss Oyster, but it is not practical so far. Okay, so if you have a permanent magnet, then we can have magnetic levitation train, lot of things. Okay, lot of motors, everything can be miniaturized. You can see like motors which are having permanent magnets, they are heavy. So if you have a lightweight magnet, then we can use it in space application, defense application, we can use it in aircraft, etc. So if you want, another one drawback is NdFeB, neodymium iron boron magnet, that is the strongest known permanent magnet, but we are reliant on China. Now, China has a lot of rare earth resources. So NdFeB, neodymium, we have to import from China. So the cost is determined not by various factors such as suppose the oil, availability of oil. So if they want to fix the price, they will fix the price. Cut the production, increase the cost. Likewise, they can do. So likewise, if you want to depend on some countries for resources, natural resources, then they will fix the price. So in order to reduce the cost, then one option is to have the nano composite, where a mixing of the soft and hard magnetic material can be done, but practically it is very difficult. Theoretically, we have done a calculation and we have shown that we can achieve 78 mgoe megagas isolated with 40% iron cobalt, okay, of 2 to 4 nanometer. So that may give rise to nearly less than 50% cost reduction if you want to make a nano composite magnet. Okay, so that is one application of nano composite magnet. Okay, so now coming to other applications, now we have also superparamagnetism. We can put forth of the positive use of superparamagnetism. Of course, now in the recording industry or in the permanent magnet industry, we don't want superparamagnetism. We don't want the moments to magnetization to fluctuate. We want stable magnetization for the recording industry and the magnet industry. But for the biomedical applications, we need superparamagnetic nanoparticles. How can you characterize the superparamagnetic nanoparticles? If through one method is like the hysteresis loop, as I have already shown you, like the coercivity will come down if your size is coming down. Okay, so in the slide of magnetic properties of Fe3O4, we have seen like when your size is reduced, you see that the coercivity is approaching zero. So nanoparticles which are exhibiting superparamagnetic behavior, they will show zero magnetization, zero coercivity. So how can you characterize it? Using the vibrating sample manometer. Another method is to use Mossbauer spectroscopy. Very simple. I'm not going into the in-depth detail about the physics behind Mossbauer spectroscopy. In Mossbauer spectroscopy, if you get a single line pattern, blue curve like this, so you say that it is diamagnetic. And if you have a double line pattern like this, doublet, it is paramagnetic. And if you have a 6-line pattern like this, a green line, then I can say it is ferro or ferri or antiferro. How can you characterize a superparamagnetic nanoparticle? Okay, so a superparamagnetic nanoparticle will give rise to fluctuation in the magnetization direction. So how fast it fluctuates? The time scale, now you see the time scale, Mossbauer effect can measure very, very small time scales. So if you reduce the size of the particle, the fluctuation also will be fast. So if you characterize the nanoparticle, you see that from the ferromagnetic 6-line pattern, your Mossbauer spectrum is collapsing to a double line pattern. So according to the fluctuation, if you have superparamagnetic nanoparticles, they are fluctuating fast. Ferromagnetic, they are stable. So stable magnetic nanoparticles will give rise to a 6-line pattern, and a fluctuating superparamagnetic nanoparticle will give rise to a double line pattern, doublet pattern. Okay, from the Mossbauer spectroscopy. So you can see an example here. Okay, so if you are fluctuating too fast, then you will get a doublet as shown here. The 20 nanometer magnesium ferrite nanoparticle, you are getting a double line pattern because of fast fluctuation. And if you are going for a smaller increase in the size, 25 nanometer, less fluctuation. Okay, so then you will have 6-line pattern also emerging. Okay, and when you are going towards very low temperature, because now when you reduce the temperature, your kb into T, thermal energy, so that will be suppressed and kV will be dominant. So you have a 6-line pattern. That are about fundamentals about magnetic nanoparticles. Now coming to the applications of magnetic nanoparticles, we will move on to the applications of magnetic nanoparticles, and I will focus mostly on the superparamagnetic applications. Okay, one application of magnetic nanoparticle is in targeted drug delivery. Okay, so you have a magnetic nanoparticle, so you coat the magnetic nanoparticle with the required drug, and selectively you can deliver it to certain regions in the body. The advantage is like so if you are having a drug which is given into the circulatory system, then it will go throughout the circulatory system. It will go to all the organs through absorption. So, and it will be even getting deposited in the liver, kidney, etc. So if you have a magnetic nanoparticle and if you coat the drug on the magnetic nanoparticle and deliver to select region, then the side effects can be minimized. For example, like no chemotherapy or a radiotherapy, it will induce a lot of side effects like hair fall, etc., etc. So you can have a local delivery of drugs using magnetic nanoparticle. So for that, we need highly magnetic nanoparticles. Okay. So next, I will just discuss one example which we have done, okay, in our laboratory. So you might have heard about Fukushima nuclear disaster. Okay. So there was an earthquake in May 11th, May 2011. So that triggered a 14-meter tsunami. So that tsunami that dredged the water, that water, no, that entered into the reactor. So the reactor was shut down and it was running with the generator. Okay. So the generator also, no, after hours, no, it also went off. Okay. So during this period, what happens? No, the fuel rod's temperature, it went up. There was hydrogen explosion. So there was meltdown and hydrogen explosion. As a result, 6 to 20 pentabecquerel of cesium-137 was released into the environment. Okay. So the atmosphere, it was as both as in the air as well as in the water, radioactive cesium was left as such. Okay. So cesium-137 has a half-life of 30 years. So we need 30 years for at least half of the isotope to die. So then the biological life half-life is 70 days. So if you are exposed to cesium-137, it will remain in the body. Okay, and for 50% of the cesium-137 to be removed, it takes 70 days. Okay. And if you have 140 megabecquerel per kg of cesium-137 exposure, you will die in a month. So that is the status of cesium-137, which is a major isotope, radioactive isotope having larger half-life, okay, when there is a nuclear accident. So people used to treat the cesium poisoning with the Prussian blue. Okay, so the Prussian blue, that will the cesium will bind with the Prussian blue, and that can be removed through our digestive system. And if you take, you can see the capsule. One capsule has around 250 milligram of Prussian blue. So that can be used for reducing the biological half-life of cesium to about 1 month. Okay. So we had a plan that no, we coat the magnetic nanoparticle with the Prussian blue, and we can detoxify or we can clear the pollutant, radioactive toxins, very easily using a magnet. So that was the idea, and that was the project which we wrote, and it was sanctioned during the year 2008-11. And you can see, during the period itself, the Fukushima accident happened. So we can have some ideas in our mind, and we can execute the idea, which may be like useful not now, maybe in the future, or when there is a natural calamity or when there is a disaster, everyone will run after that, like COVID situation. So we have to prepare, be prepared. Science and technology is for preparation for the betterment of human lives. So when you are doing something, you may think, okay, this is not useful to us. But no, in the future, it may help us. Okay. So in that sense, we try to surface modify the magnetic nanoparticles with the Prussian blue. And what is the advantage? So instead of a biological half-life of around 1 month, you can clear it within hours. So you have a magnetic nanoparticle, we can coat it with the Prussian blue, and the Prussian blue will capture the cesium, and the Prussian blue cesium magnetic nanoparticle can be removed using a magnet, external magnet. So that is the idea behind the detoxification of radioactive toxin. So this we have published quite a lot of literature. We have few of the work we are shown here. So actually the most important point is like, if you want the magnetic nanoparticle to be captured very easily, if you capture very easily the magnetic nanoparticle, cesium can be also eliminated easily. So the capture efficiency should be 100%, but we will never achieve the capture efficiency of 100%. All the 100% nanoparticle will not be captured. Okay. So if you have a velocity flowing medium, so some drainage water or some water which is polluted, then if you want to capture it, capture the nanoparticle, the magnetic moment or magnetization should be as large as possible. So using magnetite as the model, we have seen that we are achieving very good capture efficiency when the flow velocity is less. Obvious. Okay. When you increase the flow velocity, the capture efficiency will come down. Okay. But the point is, we need to do some surface modification steps. So we have to treat it with HCl and everything, and try to characterize it and see that the Prussian blue is in fact attached to the magnetic nanoparticle. Otherwise, your magnetic nanoparticle alone will come. It will not be coated with the Prussian blue. So we did some surface modification and quite successful in attaching the Prussian blue on top of nanoparticle. And we have also seen that cesium also gets attached to the Prussian blue, and we can achieve a very good capture efficiency. And unfortunately, the magnetization is poor. So you can see here, C is the point C, blue hysteresis loop. Y-axis represents the magnetization. If your magnetization is very large, it is quite good. But the magnetization is very large only when you have a very large magnetic nanoparticle. So 90 nanometer magnetite, it will show higher magnetization. Okay. And when you are having 10 nanometer, small nanoparticle, then your magnetization come down. Okay. In fact, no, this reduction in the magnetization is not due to surface effect or due to the some other phenomena. It represents that you have very good attachment of Prussian blue. Prussian blue is not magnetic. So if you have a lot of Prussian blue, then if you measure the total magnetic moment is the sum of all the magnetization. So if you divide by the weight, you will come to know that the non-magnetic fraction will reduce the total magnetization. So you have very good attachment of Prussian blue. So the point is, even with the Prussian blue, we need higher magnetization. Remember, the choice of magnetic materials are very limited. We have only selected magnetic materials. So that is one application of magnetic nanoparticles, that is for detoxification of or clearing environmental contamination. This is a very simple project any even undergraduate student can take up, even in your home setup. Okay. And next, I think there may be an introduction to hypothermia, magnetic nanoparticle hypothermia. So if you are having a magnetic nanoparticle and if it is super paramagnetic, even if there's very small applied magnetic field, you can turn the direction like this. Okay, fluctuate the magnetic direction in an applied magnetic. Okay, so that will give rise to heating. So this is the prototype of the magnetic hypothermia heating equipment, which was prototype experiment. And the heating is due to two mechanisms. One is the Néel relaxation and another one is the Brownian relaxation. Néel relaxation is the rotation of the magnetic, okay, the magnetization. Brownian relaxation is the rotation of the particle by itself. So these two mechanisms will contribute to the total heat generated by the magnetic nanoparticle. Okay, so you can see a little bit of physics here. So this was first this derivation and other things was taken from the article Rosenweig in the year 2002. So immediately after he published this paper, we started to do some theoretical simulation and theoretical experimental work. So the basic mechanism here is the power dissipation, power P from equation 2, it is frequency into energy per hysteresis loss, delta W. That is proportional to chi double prime H naught square applied magnetic field, applied AC magnetic field. Remember, in an AC magnetic field, the moments are fluctuating. not a direct magnetic field. In the vibrating sample magnetometer, we are applying a direct current magnetic field. Okay. So here AC magnetic field. So H0 is the applied magnetic field and F is the frequency. So chi double prime equal to chi naught susceptibility, initial susceptibility chi equal to M by H, magnetization by applied magnetic field. So chi naught into 2 pi F tau by 1 plus 2 pi F tau whole square. That is the equation 3. But the point is, I told you Neal relaxation time and Brown relaxation time. That will influence the total relaxation time tau. In equation 3, we have tau. That is the net relaxation, effective relaxation time. The effective relaxation time is determined by the Neal relaxation time and the Brownian relaxation time. Neal relaxation time depends on the anisotropy. What is meant by anisotropy energy? I have already told. So Neal relaxation time depends on the ratio of the anisotropy energy to the thermal energy. As per equation 5, you have K effective into V by KBT. Okay? So from that, the Neal relaxation time is influenced by the particle volume and also the effective anisotropy constant. Okay? And the Brown relaxation time, equation 6, so that is determined by eta, viscosity, hydrodynamic volume. Hydrodynamic volume means the volume of the particle plus any surface layer which is attached to it. So that volume divided by Kb. So if you have tau 1, tau b by tau 1 plus tau b, so that will be the effective relaxation time. So that will be the basic mechanism behind power dissipation. Okay, heat dissipation in magnetic nanoparticles. So from the first law, du equal to delta W by plus dW. For an adiabatic process, delta Q equal to 0. So what you have is dW I am taking as delta W from equation 1. So delta W is already there in equation 2. So if your power is large, then more heat will be generated. Okay. So more heat will be generated if you are having a high frequency as well as large delta time. So now, just seeing this, if you see the simulation here, you can see that lot of magnetic nanoparticles are there, and all nanoparticles will not generate heat. There is an optimum size at which it generates heat. That is obtained from equation number 3, effective relaxation time tau. That also has the volume from equation 5 and 6. So that will determine the optimum heat generating size of the nanoparticle. So if you are saying like FEF means that is magnetite. So that will generate heat around like 14 to 16 nanometer. So likewise, if you are having CO3, cobalt ferrite, it will generate heat below around 12 nanometer. So likewise, there is an optimum size. So you have to prepare a magnetic nanoparticle of the optimum size, which can generate the heat, and then only you can use it for magnetic nanoparticle hypothermia. Okay, treatment of cancer using the heat generated by the magnetic nanoparticle in an AC magnetic, alternating magnetic. Okay. So the power dissipation is given by delta T by small delta t, the heating rate into C specific. So if your heating rate is very large, then more will be the power dissipation. For an example, you can see like magnetic nanoparticle hypothermia. So this we have published in 2009. So we have prepared different nanoparticle sizes, and we have seen like 13 nanometer experimentally, 13 nanometer particles, which is having a saturation magnetization of 64 EMU per gram and a coercivity of 6 Oersted, will give a specific absorption rate. SAR is specific absorption rate of 16 watt per gram. The SAR is defined here. It is proportional to delta T, that is the temperature difference, divided by time difference. So more power dissipation means more will be the SAR. For a comparison, if you are taking a mobile phone and speaking, of course, it is harmful because of only the heat. Okay. So if you are going for a high frequency, then it is more harmful because it will produce electromagnetic waves which damages the DNA. So if you are taking a microwave oven, if you are heating it, That is a microwave which is having a low frequency but higher wavelength, but that will give rise to heating. A similar effect will happen if you just speak for hours. If you speak for hours, now your ear will get heated up. So the SAR limit, the prescribed SAR limit is 80 microwatt per gram. Now you can compare the SAR limit, okay, allowed SAR limit with the magnetic nanoparticle, which is generating a SAR of 16 watt per gram, which is quite large. Okay, so that is useful for treating the tumors or cancers. Okay, so you see here the size effect of magnetic nanoparticles that was published in the year 2019 by my scholar and myself. And you see here the thermography images, thermal camera. So A is the heat generated by the magnetic nanoparticle at a time period 5 seconds. And B is the time period of 145 seconds. You see that now the heat generated is increasing with time. So with time, you get heating. But only when you have an optimum size of around 10 to 12 nanometer. So you see here in the left curve, you see that 60 nanometer particle is not same magnetite. 60 nanometer is not showing any heating rate with the time. Okay, with the time delta T by delta small t is not increasing with the time. Okay, so you see that no, for a 10 to 12 nanometer particle, with respect to time, your temperature is delta T is also increased. So you see that optimum size is required. Okay, and remember, if you inject this and if you apply a magnetic AC magnetic field, and with the time it increases, and maybe you have to be careful enough so that no, it is not destroying the normal tissues also. So this is another recent results where we have also seen like the experimental and theoretical heating rates of cobalt ferrite and nanoparticles. And you see here the theoretical heating rate is around like 6 to 8 Kelvin per second, which is matching with the experimental value. So the previous publications, initial publications, the heating rate was very, very large, around 600 Kelvin per second. That was theory, but it was not achieved in practice. So most of the reports, even now, they say no, heating rate may be around 600, at least 300 Kelvin per second. But no, practically you will not get that much heating. Okay, due to different factors such as the particle density, dipolar interaction, etc. Here you can see an example. Okay, the light pink colored CO3 that is showing low heating, delta T, temperature difference between room temperature and the heating with the time. Okay, so that is low in the same cobalt ferrite. Okay, CO3 and D2CO1 are same material. So if you coat CO3, okay, with a surfactant such as dextran, then due to dipolar interaction, your heating goes up. So it is not quite simple that heating is any nanoparticle, by any nanoparticle or any condition you can get heating. It is not very simple as that. You have to choose the optimum size. You have to choose the external factors, particle density, etc. Okay. If you load too much of nanoparticle, that is also disastrous. You cannot load too much nanoparticle because that will be giving some time for clearance. You need body will clear the nanoparticle, so it will be toxic if your body is overloaded. And also now, if you are going too low nanoparticle, it will not produce sufficient heat. Okay, and if you are giving too much nanoparticle, then too high heating also will destroy the normal tissue. So optimum choice is required. Still, it is under experiment. That is why even after years of experimental research, it has not gone to the clinical stage because of various external factors which are influencing the heating rate. Okay, so we need reproducibility, repeatability, stable heating. So all these are required. Biocompatibility is required. So but thing is like there are promising results, both biologists, given by both biologists. Okay, so there may be future applications. Remember, when this is used for treatment of cancer, this will be the low cost and least expensive. Okay, least expensive as well as least side effect. There will not be practically no side effect because of heating. Then these are some of the future concepts. Like no, so far no, you cannot use magnetic nanoparticle for stroke and heart attack cure. No, due to clot, no, there may be a heart attack. Okay, so if you want to cure that, then if you give a medicine like a strong medicine, then again no toxicity will increase. So if you can explore like no coating the magnetic nanoparticle with a drug, strong drug, which can deliver selectively be delivered into the clot. After extensive literature search, I have identified these things, this drug to be coated, which can be taken as a project by any of you. Maybe if you need guidance, you can contact me, no problem. Okay. So another future concept is like is to use magnetic nanobots for arterial declogging. So if there is a like a buildup of plaques, okay, in the blood vessels, so your blood supply will be stopped. Then immediately there will be a heart attack like that. It was so famous actor died because of 100% blocking. Okay, so suppose now if your blocking is like 60% or 70%, then what doctors do, they will do an angio, okay, or they can do a bypass. Okay, so if you want to do a side effect free and no hospitalization and without surgery, if you want to think about cheapest method, then you can use this future concept of using magnetic nanoparticle. Okay, so you can like a corkscrew like arrangement where you can rotate the magnetic nanoparticle in an applied magnetic field, AC magnetic field, and try to declog. Okay, so this is a future concept, and of course, the microbots is available. So in the future, it is not like long term to go. So in the future, you may see these type of developments. Okay. So next one is highly magnetic nanoparticles. If you have, then you can use it for magnetic field assisted maneuverability. Okay. So remember, I have told you about magnetite, which is used in hypothermia. So you want to deliver that magnetic nanoparticle to the selective region, and then only you can do the heating. And you have to see that it is remaining there. So you can deliver it using a external magnet or using some guider, etc. But you need a strongly magnetic nanoparticle. So that means your magnetization should be large. Magnetite has a maximum magnetization of 90 EMU per gram. And when you reduce the size of the nanoparticle, as I have already explained to you, your magnetization comes down. So you need highly magnetic nanoparticle for delivery, maneuverability. So that means already this capsule endoscopy is available in the market. It has been developed less than 5 years. So you can instead of putting a endoscope into your mouth, through your mouth, and examining the intestine or esophagus, what you can do is you can swallow the capsule, and it will have a tiny camera, and that tiny camera will monitor if there is any ulcer or any other damages available. So if you are having a magnetic maneuverability, that means if you can control this camera using a magnet, then you can very well examine the body internal organ, okay, very easily. Otherwise, there is a chance that this camera will get stuck up and it will be held up, okay, for maybe even 1 year, 2 year, or 3 years. And again, we may require a surgery in order to take this out, which is unnecessary. Okay. So if you have a magnetic maneuverability, then we can use a magnet and we can take it out. So that is an advantage, for which we need highly magnetic nanoparticle. For hypothermia, we need highly magnetic nanoparticle. For drug delivery, we need highly magnetic nanoparticle. For maneuverability, we need highly magnetic nanoparticle. Okay, so there are a lot of potentials in these areas. Then again, no, in MRI, we inject a contrast agent and we can see the parts, body parts very clearly using the contrast agent. There are two types of contrast agents, that is no T1 and T2 contrast agents. T1 contrast agents, now you can see here, water is dark, fat is light. The opposite thing happens in T2. So if you want to see any brain tumors, then you have to inject the contrast agents into the tumor region, and then we can examine it. So for which we require a magnetic nanoparticle as a contrast agent, that is T2 contrast agent. The basic mechanism is spin transverse relaxation, and this is a negative contrast agent. So for which we require magnetic nanoparticle. Okay, so gadolinium chelate, that is a T1 contrast agent that has more side effect compared to magnetite. Magnetite is composed of iron in the ionic state. Okay, so that is no. You have hemoglobin which has iron in it, so we have biocompatibility with the iron oxide. So next, this is one of the recent development, how magnetic nanoparticles can be used in COVID detection. So you can have magnetic nanoparticle which is coated with the protein. Protein is known as now protein A coated. So this was recently published by one of the researchers from China. So they use magnetic nanoparticle coated with the protein, and when the virus stimulant, so when it gets attached, the rotation of the particle is slowed down. So we know there is a relaxation, Neal and Brownian. Brownian relaxation is the rotation of the particle, right? So when the virus gets attached, then what happens? The rotation is slowed down. So that will change the Brownian relaxation time. That is monitored. And when you are having more coronavirus, then the time, that is the Brownian relaxation time is altered as shown in the bottom graph. So in that sense, now we can use, but this is not matured. This is only demonstrated by one of the groups from China. Okay, so it requires a lot. It is in the initial stage. Okay? So with this, I just summarize by telling you that we have a lot of potential in magnetic nanoparticles for biomedical application. So if one door closes, another door opens. The door closed for recording, but the door opened for biomedical applications. So what is the future direction? We need highly magnetic nanoparticles. So far, people are using magnetite. So what is the choice? So if you scan through the literature, you see that you have highly magnetic materials such as iron cobalt, which has the strongest magnetization close to 240 MeV per gram. Then comes iron, okay, around 220 MeV per gram. Then cobalt, then Fe3O4. You see magnetite, Fe3O4, it is only around 90. Then nickel. So if you use iron or iron cobalt, it will be far, far better. But the problem is the stability. What happens now if you prepare the magnetic nanoparticles of iron or iron cobalt? It will oxidize to iron oxide. So your magnetization again comes down. So as of now, your material is not stable. Okay. Forget about how to prepare. There are also problems with the preparation. How will you prepare iron? Even if you leave an iron open, it will rust. You can see grill gates, etc. It will rust. So if you have prepared a very small nanoparticle, your surface area is very large, high reactivity will be there. So it will oxidize immediately. So one promising technique to prepare metal nanoparticles is polyol process. Remember, I am just introducing the chemistry. Here, one method to prepare nanoparticles, metal nanoparticles, it is a polyol process, which is nothing but a polyol, which is ethylene glycol, propylene glycol, etc. You put the precursors hydroxide or chloride precursors into the polyol, heat it, you will get the metal. So that is a very simple process, which is successful in the preparation of gold. Any material which is having a standard reduction potential very high, that can be easily prepared using polyol process. So you see here, this was published by us. Actually, the polyol process was first invented by Five et al. In 1989. So here, no, in our analysis, we see that if your standard reduction potential is high, as in gold, you can easily prepare gold, okay, using polyol process. But if you see iron, we need highly magnetic particles such as iron, not diamagnetic materials such as gold. So you see the properties of gold, when it becomes nano, the color changes from yellow to blue. Okay. So if you are having a highly magnetic nanoparticles such as iron, then we can use it for further biomedical applications. So one promising technique is polyol process. Okay, so in fact, we succeeded in synthesizing, preparing iron. Not only iron, prepared iron in 2007 and prepared iron nanoparticles in 2010. But as expected, the iron nanoparticles, there was a shell which is oxidized iron oxide. So you have a core which is iron, and at the surface you have iron oxide due to oxidation. But we are quite happy that you have iron inside and you have a surface iron oxide. The advantage is you will have high magnetization, as well as you will have biocompatibility due to the iron oxide, because iron oxide is very well established to be biocompatible compared to other nanoparticles. Okay, so now you have a surface oxidized iron which is stable. Okay, when you reduce the size, it is becoming oxidized, and you are having a core shell cell morphology. Okay, and your magnetization, if you measure the magnetization, so this has been quite recently studied by us, the magnetization as well as the coercivity variation with the size. Okay, so when you are reducing the particle size, reactivity increases, so you are getting oxidation, iron oxide on the surface. So as a result, your magnetization is coming down, down, down. So when you are bringing the particle size much smaller, your magnetization is also coming down. But the advantage is this magnetization is higher than the commonly used magnetite. So this is the future potential. It has future potential. Like we have highly magnetic iron, which is quite stable, and as well as there is a core shell, so which can be used for biomedical applications. Okay, so now, as I have already mentioned, another choice is there. What about iron cobalt? Iron cobalt has higher magnetization than iron. So then what about preparing iron cobalt? Okay. So if you prepare iron cobalt, then we can be quite successful that say that we have the nanoparticle which can exhibit higher, at least theoretically, which can be the highest saturation magnetization. So iron cobalt, remember, iron has a lower magnetization than iron cobalt. Cobalt has a lower magnetization than iron. But if you combine iron and cobalt, okay, that is showing a higher magnetization than both of them individually. So that is due to the density of states. That is a little bit of fundamental thing. So when you have unpaired electrons, because in metals and alloys we have free electrons. So if you then comes the density of states, density of free electrons. So when you have unpaired electrons, density of states at the Fermi level, which is higher, then we will have a large magnetic moment. So that is the case with the iron cobalt. So then we try to prepare iron cobalt. So we are quite successful in preparing iron cobalt, and that was published earlier in 2006, advanced materials. But now, this iron cobalt, which we prepared by one of my scholars, it showed a flower-like morphology, like a cubic flower when it is iron rich, and it is a spherical flower when it is cobalt rich. What about the magnetization? What is the potential of this nanoparticle? here, no, I can say like, no, you are having small structures which are in the nano regime. So I can say this is a nanostructure. Okay. We can use these nanoparticles or nanostructures for catalysis, more surface area. So catalysis, EMI absorber, steep technology. We can use it for environmental remediation. So these are a lot of future applications which we can think about using highly magnetic iron cobalt based nanoparticles. Okay. So in addition, like no, we have also studied the fundamental structure and magnetic correlation of iron cobalt nanoparticles. So it is the core is ferromagnetic. The core, what is the core? Core is iron cobalt. There is a surface layer, oxide shell, which is superparamagnetic. So you have a sextet, which is ferromagnetic from the core, and a doublet, the central dip, no, that is a doublet. So that is having a superparamagnetic relaxation that is coming from the surface. So core is ferromagnetic, shell is superparamagnetic. So that is the behavior of the iron cobalt nanoparticles that was published. Okay. And if you see the magnetization of the flower-like nanoparticle, it is 186 mu per gram, which is quite high. Remember, in the iron oxide, Fe3O4, even the bulk is only 90. So we are having more than double of the magnetite. So this has tremendous applications in the future in the field of biomedical. And how we have confirmed all these stories come from these characterization results. Whether we have truly obtained the nanoparticles, whether it is iron cobalt or something else, that can be verified from the characterization. So convincingly, we have characterized everything and we have proved 100% that no, it is iron cobalt alloy, okay, and not something else. Because no, sometimes if you try to prepare some nanoparticle, you will end up in something else. So you have to be very careful in characterizing the nanoparticle. So, and also when you make the iron cobalt to very small size, when you reduce to very small size, again we are seeing that now we have an iron cobalt core and a gamma Fe2O3. It is also ferrimagnetic when you are going beyond below a temperature known as the blocking temperature, and above the blocking temperature, above the temperature at which it becomes superparamagnetic. So thermal energy KBT is the thermal energy competition and K with the KV, anisotropy energy. Okay. So when you are going towards a higher temperature, that means there are more chances that it can become superparamagnetic. So at what temperature it becomes superparamagnetic? So that temperature is the blocking temperature. So below the blocking temperature, if you measure, we can easily characterize using Mossbauer spectroscopy. You will see a 6-line pattern, which is from the ferrimagnetic state of the gamma Fe2O3, and above a blocking temperature, and or if you see the room temperature, you see a doublet, that is superparamagnetic. Okay. So now this has been published, and what is the application of this? One such application is in in exchange bias. What is exchange bias? The shift in the hysteresis loop. So you may have seen the hysteresis loop as symmetry. All the sides are similar. But no, if you are having a ferromagnetic core and an anti-ferromagnetic shell, then what will happen? The ferromagnetic means up direction, anti-ferromagnetic, one will be up, another will be down. So the down spin will couple with the up spin. That is, the core is ferromagnetic, which is up. That will be ferromagnet with the up spin will be coupling with the down through exchange interaction. Okay. Remember exchange interaction term J. So that will couple and that will give rise to stable magnetization. So if you are having a superparamagnetic nanoparticle, that will be fluctuating. But if the moments, if they couple, that fluctuation can be overcome. You can have a stable magnetization. So you can destroy or kill the superparamagnetic effect with some core shell structures using the phenomena of exchange bias. But the problem is, we don't have exchange bias at room temperature. We need applications at room temperature. So you see, exchange bias temperature, blocking temperature is going below 50 Kelvin. So below 50 Kelvin only, now you are getting this exchange bias phenomenon. If you are getting above 300 Kelvin, then that will be very good. Okay. So that is some of the application. So summarize, in summary, what are the prospects, emerging, what are the emerging areas of applications? Like, you can have a 600 kilometer per hour maglev train. Magnetic levitation train will have tracks made up of permanent magnets. So if you want permanent magnets, we need strong magnets. Okay, so if you lay a track 600 kilometer per hour maglev train with the tracks from Chennai to Kanyakumari, you just remember the cost. Imagine the cost. It will be quite expensive. So we don't have a strong permanent magnet which is low cost. We have to import all the stuff from China. So if you have a high energy product permanent magnet, then we can have a high speed, low cost train. According to my prediction, it will take another 50 to 100 years to realize that. Practically realize. Technology is available, but the cost is preventing us. So magnetic field control is not quite simple as shown in movies. Because no, you are so the force experienced by magnets, so it is like no square force, 1 by square force, 1 by r square. So when you bring much closer, like when you are too close, then only strong force will be felt. So you at a kilometer distance, or some meters distance, you cannot pull. You can experiment this with the power magnet in your home. So you can have some realizable practical applications in the near future, but the most important application may come in the medical field, and I predict that it may come in around 5 to 20 years. 5 years it will start, and 20 years it will mature. So in the future, you need not go to the hospital, but you may have nanobots which can inject drugs into our body, and which can be monitored online through artificial intelligence, and if necessary, doctors may intervene. That is the future prediction. And in place of magnetic nanoparticles, as far as the magnetic nanoparticles are concerned, what we require is maneuverability, that is easy maneuvering, and it can be used in diagnosis and therapy. There are a lot of potentials, but only thing is we need now highly magnetic nanoparticles, which are still being in the nascent or early stage of research. So with this, I summarize. So magnetic nanoparticles, which can be synthesized through chemical methods. One method I have explained you, metal nanoparticles, Fourier process, and highly magnetic core shell nanoparticles you can prepare. That will be the future for a variety of nanoparticle based applications, especially in the medical field or biomedical applications. So there are a lot of research scope in the biomedical application area, but it is a highly interdisciplinary topic which requires both physicists, chemists, biologists, all of them to be coming together and share their knowledge. And I wish to acknowledge my collaborator, Vinesh, my supervisor during PhD, Professor Narayanasamy, then my postdoc supervisor, Professor Jayadevan, my PhD graduates, both are abroad, and my scholars present now, they are also undergoing research. Few of the research work I have also presented. Of course, the most foremost, I appreciate DST, and I thank DST for the funding. If it is not there, no, I may not have done this type of work. So thank you for listening to this work. And if you have any questions, I will be pleased to answer. Thank you for.
Thank you very much, sir. And now, dear participants, it's time for interaction with the resource person. You may use the chat window to key in your questions if you have to get clarified, please.